Limits, an introduction.
Alright, so let's take a look at this informal definition of a limit. And we're actually not going to cover the formal definition of a limit, which involves epsilons and deltas, because it's outside the scope of AP Calculus. So we're going to go through this definition step by step. So suppose f of x, some function, is defined on an open interval about c, except possibly at c itself. So let's stop right there and try to look at the picture and see if we can make sense of that first part. So suppose some function is defined on an open interval about c. Well, c is going to be an x value. So on this image here, c is on the x-axis, and we want an open interval. So let's just create ourselves some little open interval about, which means around, my c value. And what we want to happen is we want the function f of x to be defined on that open interval. So what that means is that for every x value in this little open interval I choose, there's a corresponding y value. That means the function is defined. So I'm defined all along the curve, except possibly at c itself. So it's possible that at c, the function is not defined and there's an open circle. Well, this function that I've shown here is defined at c. There's a filled in circle. So this is just a curve that keeps going and there's no missing function value at c. So this second image here shows that possibly at c, the function may be undefined. So we could create an open interval here and say that the function is defined everywhere in this interval except at c itself. Now let's continue. Now if f of x, if the function is arbitrarily close to L, so let's find L. L is on the y-axis. So if the function gets closer and closer and closer to L, some y value, for all x sufficiently close to c. And this is why we call this an informal definition, right? So we use arbitrarily close and sufficiently close. So this is not an exact definition. So what's happening is, as we get really, really close to c on the x-axis, so as I head towards c on the x-axis, are all of my y values, are they all going towards the same number? So in this case, we're calling that number L. So as I move closer and closer in from both sides, am I getting closer and closer to some number L? Now, if it is, then we say that the function f, or f of x, approaches the limit L as x approaches c. And we write it in the following notation. So LIM, standing for limit, x approaches c, so approaches is turned into this little right-hand arrow, and the arrow always faces to the right. So the limit as x approaches c of the function f of x equals L. So as I get close to some particular x value, we call that x value c, from both sides of c, if I get close to some particular y value on the function, then we go ahead and write that the limit as x approaches c of f of x equals that number L. And it doesn't matter that there was a filled in circle on this second graph, because as I get close to c from both sides, well, my function's still getting arbitrarily close to this y value here, L. So it didn't matter if there was an open circle there or not, because limits don't care what happens at that particular value. They care about what happens as we get close to that particular value. Alright, so now let's take a look at an example of an actual function. So we're not just going to deal with f of x. F of x in this first example is going to be the function sine x divided by x. And we want to look at this function near x equals 0. So we're not going to care about what happens at x equals 0. And this is actually an interesting problem, because notice that at x equals 0, so when we substitute 0 in for x, f of 0 would be sine 0 divided by 0. Well, sine 0 is 0, and on the bottom I have 0, so I have 0 over 0, and that's undefined. So at 0, we can't even really determine a function value. The function is undefined. So instead, we're going to look at values near x equals 0 from both sides of 0. So let's go ahead and take a look at these two tables. So this is considered to be a numerical approach to evaluating limits. So when I say a numerical approach, it means we're going to create a table of numerical values. So we're going to substitute into the function, into sine x over x, we're going to substitute in values that are pretty close to 0 from both sides of 0. So from the left side of 0 and from the right side of 0. So on the number line, so just real quick in the center here, let's say I have the number line and it's the x-axis, so here's 0. To the left side of 0, well, I would probably think the first number I want to try is -1. I guess that's sort of close to 0. So if I substitute -1 into sine x divided by x, using my graphing calculator, I'm going to arrive at the value 0.841470985, and this is going to continue on and on. So I'm just going to stop right here. These are all the values my calculator has shown me. Alright, so now I want to figure out, well, what happens when I get even closer to 0? So what's closer to 0 is -0.5. So at -0.5 or -1/2, when I substitute -0.5 into sine x over x, I'm going to get 0.958851077. So what I do is I just keep getting closer and closer to 0 from the left side. So what's even closer than -0.5 is -0.1. And here's my next value is 0.998334166. Then I'm just going to keep going, and I'm going to plug in -0.05, and then -0.005, and then -0.001. So -0.001, that is pretty close to 0 from the left side of 0. And what's happening here? So if you notice, as I continue to get closer and closer to 0 from the left-hand side of 0, I'm arriving at a number that's followed by more 9s after the decimal place, so 0.999999833. So this number is getting closer and closer to the whole number of 1. So as I continue to extend the 9s past the decimal, I'm getting closer and closer to 1. So what's happening here, how we would read this, is x approaches 0 from the left-hand side. So as I approach 0 from the left, as x is approaching 0, it looks like that the y values in this right column, that they're getting closer to 1. So now, once I've analyzed one side, I'm going to go ahead and see what happens on the right side of 0. So to the right side of 0, well, 1 is probably the number I'm going to try first. So when I substitute in 1, I get now 0.841470985. Well, that looks familiar when I plugged in -1. And then when I plug in 0.5, you'll notice I get the same answer as when I plugged in -0.5. And if I go ahead and continue to look at my graph, or look at my function values in this table, I can see that as I approach from the right side of 0, 0 from the right-hand side, I still get closer and closer to the positive whole number of 1. So looking at the very bottom here, I'm going to introduce you to some new notation that we're going to see again in the next video. So x approaches 0 from the left. So we indicate from the left to be with this little negative sign up where an exponent would be. And then what's happening as I approach 0 from the right-hand side, that little plus sign in the upper exponent means what's going on from the right side of 0. So what's happening is that those y values are getting closer and closer to 1. So what does this mean? What can we conclude? So from this, we can guess that near x equals 0, the function gets arbitrarily close to, it gets closer to 1, or f of x approaches or converges to 1. So why do I have guess underline? Because unfortunately, a table of values, a numerical approach to limits, only gives us a pretty good idea of what the limit might be. But we can't say for certain that the limit equals 1. Alright, so now let's take a look at a graphical approach to evaluating limits. And we're going to analyze the same function. We're going to analyze sine x divided by x. And we're asking, well, what's happening to the y values of the function as we are approaching x equals 0? So here I've provided the exact graph of sine x divided by x for you. And we're interested in what's going on near 0. And on this particular graph, at 0, the function sine x over x is not defined. There's a hole in the graph. And remember what happened when we substituted in 0? we got 0 over 0, which is undefined. So notice we do have that open circle in the graph. But just a warning, if you were to graph this on your graphing calculator, it doesn't show you holes in the graph. Your graphing calculator doesn't show you holes in the graph. So this graphical approach to evaluating limits is also not precise unless you're explicitly given the graph like this. So just like the numerical approach gave us a pretty good guess, the graphical approach is also going to give us a pretty good guess unless you're specifically given the graph as I've given it to you here. So what's happening to the y values as we're getting closer to 0? So as we get close to 0 on the x-axis, we ask ourselves what's happening with the y values on the function. So the function's the blue curve. As I get close to 0 on the x-axis, my function is getting closer and closer to 1 on both sides. So it looks like this limit or this graph matches the information we got on our table of data. So it looks like as we get close to 0 from both sides, our function is approaching or getting closer to 1. So what can we conclude? This graph is going to support our guess that as x approaches 0, from the left and from the right side of f of x, we approach 1. So from the numerical and the graphical evidence, it seems reasonable to say that the limit as x approaches 0 of sine x divided by x is 1. So in limit notation, the limit as x approaches 0 of sine x divided by x equals 1. Alright, let's take a look at another example. So this time we're going to look at the function f of x equals x squared minus 1 divided by x minus 1. And we're going to look at this function near x equals 1. So in other words, we're going to use a numerical and a graphical approach to approximate the limit as x approaches 1 of the function x squared minus 1 over x minus 1. So remember, for limits, we don't care exactly what happens at the function value. But let's just go and take a look at what happens there anyway. So when I substitute 1 into the function, so what is f of 1? F of 1 is 1 squared minus 1 over 1 minus 1. Well, 1 squared is 1, so 1 minus 1 is 0. 1 minus 1 in the denominator is 0, so again we get undefined. So we're going to get another hole in the graph here. We're not even defined at this particular value near 1. But looking at a numerical approach first, we can figure out what's happening around 1. So again, on a little number line, if we think about 1, and we think about numbers on the left side of 1, but really, really close to 1, let's go ahead and try something really, really close like 0.9999. So notice that's one of the x values I've chosen in my table. So my table this time, I'm going ahead and letting it be horizontal. So we can think about 1 being sort of in the center of this table. So notice 1 isn't included in the table, and we know what happens at 1, we're undefined. But to the left side of 1, we substitute in 0.9999, and we get out a function value, 1.9999. And then a little bit to the left of 0.9999 with 4 nines after the decimal is 3 nines after the decimal. And we get out a function value of 1.999. And we can keep going. So 0.99, 1.99, and then 0.9, 1.9. So we can see that as we look, as we get closer to 1 from the left side of 1, so 0.9 is the number that's furthest away, and then I'm getting closer and closer, what does it look like is happening to my y values? Well, my y values look like they're getting closer and closer to 2, right? So as I continue to extend with nines past the decimal, I'm getting closer and closer to 2. And now if I look at the right side of 1, so I don't want to go ahead and plug in that whole number of 2, because 2 is to the right of 1, but remember, I want to know what's going on arbitrarily close to 1. So I want to stick with numbers like 1.1, 1.01, 1.001, 1.0001. So now I'm getting closer and closer to 1. So 1 in this case would be over here. So I'm getting closer to 1, but this time from the right side. So as I start to plug in values from the right side of 1. So 2.1, 2.01, get closer and closer to 2. So as x approaches 1 from the right side, I'm getting closer and closer to 2. So since I got closer and closer to the same y value, so 1.99 is pretty close to 2, 2.01 is pretty close to 2, we can guess, because we're only doing a numerical chart, that near x equals 1, the function gets close to 2, or f of x approaches or converges to 2. So now we've analyzed this function near 1 with the numerical approach. So let's take a look at a graphical approach. So with our graphical approach, we're going to do this by hand. We're not going to use our graphing calculator. So notice that x squared minus 1 over x minus 1, that the numerator factors to be x minus 1, x plus 1, the difference of squares. So the x minus 1 linear term is going to cancel. And when that happens, hopefully you recall that there's going to be a hole in the graph at x equals 1, at the x value that will make each of these 0. So there's going to be a hole in the graph at x equals 1, and when these two cancel, the graph I'm going to go ahead and put down is the graph of x plus 1, except at 1 where there's going to be a hole. So this red line here is the graph of x plus 1, so it's a linear function. It has a y-intercept of 1 and a slope of 1. But right at 1, I'm going to have to draw a hole in the graph. So how do I know where the y value is to the hole in the graph? I'm going to substitute 1 into the simplified function. So 1 plus 1 equals 2. That's how I knew that at 1 I was going to have a y value of 2. So that's where the hole is going to be, not necessarily the function value. At 1, there is no function value. So if this is my graph and I want to analyze what's going on near 1, so as I get close to 1 from both sides of 1, what's happening to the function? What am I getting closer and closer to? I'm getting closer and closer to a y value of 2. So that supports my numerical evidence that the limit as x approaches 1 of this function here is 2. So we can go ahead and summarize that. This graph supports our guess that as x approaches 1 from both sides, the left and from the right, that the function approaches 2. So it's reasonable to conclude this limit notation, the limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. So at this time, you should be comfortable reading this aloud and using the proper terminology. So limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. Okay, so now let's take a look at our first theorem. A theorem is just a fancy way of saying an important result. So this important result is about two different limits that you should know. So this says that for any constants are just numbers. So for any constants, k and c, so these are variables that represent numbers, the limit as x approaches some constant c of a different constant k equals k. And the limit as x approaches c of x equals c. So it's always a little trickier to understand when there are variables involved. So let's go ahead and look at a numerical example and a corresponding graph. So in this first example, let's imagine the problem was asking us to find the limit as x approaches 2 of 4. And let's assume we don't know that the answer is 4, even though it's written here for us. So the limit as x approaches 2 of this constant function 4. Well, that's graphed for us here. 4 is just a horizontal line, so this is the function y equals 4. So if we didn't know this theorem, if we just try to solve this limit on the left, well, I have to take a look at what happens on the left and right side of 2. I have to look at the function and see, well, am I getting close to any particular y value? So from both sides of 2, from the left and from the right side of 2, on the actual function, my y values are getting closer and closer to. In fact, they are always an output of 4, no matter what. So by my informal definition of a limit, the limit as x approaches 2 of 4, well, what am I getting arbitrarily close to? I'm getting closer and closer to 4. So this limit equals 4, which matches what the theorem says. So c in this case would be 2, and then 4 is the constant k, so this had to equal that k constant, it had to equal 4. And the second example corresponds to the limit as x approaches some number c of x equals c. So x is a function that we should recognize. y equals x is the identity function. So it's called the identity function because whenever you plug in something for x, you get out that exact same number for y. So you plug in 1, you get out 1. You plug in 2 for x, you get out 2 for y, etc. So on the bottom here, the limit as x approaches 3 of x, so if we were trying to solve this problem, we didn't know the answer was 3. Well, again, we look at what's happening on the left side and the right side of 3 on the function. So on the function, I'm getting closer and closer to 3 from the left side, and from the right side, I'm getting closer and closer to 3, which was the same input value. As I was getting closer to 3 on the x-axis, I'm getting closer to 3 on the y-axis, which matches the result of our theorem. So notice that this c value ended up being the result when the function was just the identity function x. So the limit as x approaches 3 of x equals 3. So a lot of people who try to just memorize this end up getting it mixed up, but it really helps if you understand the concept and the graphical representation of the theorem. Alright, so we went through this whole lesson on limits, but the main question is, why do we need limits? So when studying some function, y equals f of x, and that's what we do in this class, we study functions, because everything in life can be represented by a function. Sometimes we only know how a function is behaving near a particular point, x equals c, but not necessarily at that particular point. So that question, the main question becomes, what is happening to the y values when I get close to some x value? So if all the y values are getting close to some number, as we get close to our x value c, then we say that our function has a limit as x approaches c. So we need limits because we may not always know exactly what's going on at a particular point, but we might know enough about what's going on around that point, and that will be able to tell us information about that particular function. Alright, now let's define a one-sided limit. So when x approaches some number c from the left-hand side, so from the negative side, or when x values are less than c but getting closer to c, we are considering the existence of a left-hand limit. And the notation is the limit as x approaches c, and then this little negative sign is read from the left. So this negative in the exponent, the limit as x approaches c from the left of f of x. And we can do the same thing from the right-hand side. When x approaches the number c from the right-hand side, or from the positive side, so when x values are greater than c, we are considering the existence of a right-hand limit. And that is denoted with a little plus sign in the exponent, and it's read the limit as x approaches c from the right of f of x. So let's take a look at an example. And the best examples for considering one-sided limits is piecewise functions. So let's go ahead and take a look at this problem. We have the piecewise function f of x equals 5 minus x squared when x is less than or equal to 2, and x minus 5 when x is greater than 2. So this is a piecewise function that you should be able to graph by hand. So 5 minus x squared is a parabola that's facing down because there's a negative in front of x squared, and it has a y-intercept of 5. So here, this is the parabola that is defined for x values less than or equal to 2. So that's why there's that filled in circle. And then it's the line x minus 5 when x is greater than 2. So this line over here, when x is greater than 2, that's why there's this open circle. We have just this linear piece to the function. So here's the graph of this piecewise function. And then here's a table of data that's going to allow us to analyze both from the right-hand side and the left-hand side of 2. So we want to consider what's happening at 2. So as my x values, so here is my x column where I plug in 1.9, 1.99, 1.999, etc. I'm getting closer and closer to 2 from what side? From the left side of 2. So here's 2. If I substitute in 1.9, so where is 1.9? It's to the left, so it's obviously not right in the middle, but my pen's a little bit thick. So 1.9 is to the left of 2. So I'm getting closer and closer to 2 from the left in this column. So what's happening to the function? Well, I have to make sure that I substitute in these x values into the correct function. So notice over here to the left, what function am I substituting the values into? Well, I have to substitute them into the top function, 5 minus x squared. That's the only one defined when x is less than or equal to 2. So when I substitute in these values, these are the y values that come out. So 1.39, 1.0399, etc. So notice that the zeros are continuing past the decimal to extend. So that means that this function is getting closer and closer to 1. So the f of x values are approaching 1. So we need to check what's going on as I approach 2, the x value, from the right-hand side. So to the right of 2 are numbers like 2.1 and 2.01, etc. And this time I have to make sure to substitute them into the other function, because now if I'm to the right of 2, now we're talking about the linear function, so I have to substitute it into x minus 5. So when substituting in 2.1 to x minus 5, we get negative 2.9, negative 2.99, etc. So these numbers on the right are getting closer and closer to negative 3. So negative 2.9999 is getting closer to negative 3. So in limit notation, here's what we have. The limit as x approaches 2 from the left. So from the left side of 2, let's change colors here. So from the left side of 2, where are the y values going? They're going to positive 1. So the limit as x approaches 2 from the left of f of x equals 1. And the limit as x approaches 2 from the right, so now as I'm getting closer to 2 from the right-hand side, where are my function values headed? Well, they are headed to negative 3. So the limit as x approaches 2 from the right of f of x equals negative 3. So the last thing we're going to notice is that the limit from the left does not equal the limit from the right. This brings us to a theorem. This theorem says that the limit as x approaches c, so not from the right or from the left, just the limit as x approaches c of f of x equals L exists. So the limit as x approaches c exists if and only if the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, and both of those limits from the left and from the right if they equal L. So the easier version of this, because this is full of terminology a little bit, says that a function f of x has a limit as x approaches c if and only if the limit from the left and the limit from the right are the same. So the limit from the right of c equals the limit from the left of c. So the if and only if part means it goes in both directions. So if, I'm going to use really shorthand notation. So if limit left equals limit right, limit exists. The two-sided limit exists. If the limit exists, limit left has to equal limit right. That's what if and only if means. It means it works in both directions. So in the previous example, what is the limit as x approaches 2 of f of x? Well, the answer is that the limit as x approaches 2 of f of x, it does not exist, which can also be written as dne. So why doesn't it exist? So a two-sided limit only exists when the limit from the left, so the limit as x approaches 2 from the left of f of x, would have to equal the limit as x approaches 2 from the right of f of x. Well, we said that 2 from the left, that answer was 1, and 2 from the right was negative 3, and those two are not the same. So that means that the limit coming from both sides, the two-sided limit, must not exist. So now let's take a look at all the ways that a limit can fail to exist, and we're going to call these the non-existent limit conditions. So we're going to say that the limit as x approaches c, the two-sided limit of f of x, does not exist if any one of the following conditions are met. If the function f of x jumps at x equals c. So what we mean by that is that following function was this little parabola, and then the function jumped down and became the linear function. So when there's this jump in the graph, we can say that at that jump value that the function's limit does not exist. The second way a limit can fail to exist is if the function f of x oscillates too much. So we're going to put that in quotes. Oscillates too much near c, so that the values of f of x do not stay close to any one number. So the best way to think about this is an example. So near 0 here, so here's 0, here's this function which is sine of 1 over x. And we say that this function oscillates way too much near 0. So if we were to try to create a table of values, a numerical approach to this limit, and we substituted in values to the left and to the right of 0, so here's this table that's created, and you take a look at the y values, they're jumping all over the place. 0.5440, 0.9129, and then jumps to a negative number, 0.5064, then 8.8269. They're just all over the place. Now, it's okay for the numbers to bounce back and forth between positive and negative as long as they're getting closer and closer to the same number. But these numbers are just all over the place. So this function oscillates too much, and we can't say that f of x gets arbitrarily close to one number L, so the limit does not exist. The third way a limit can fail to exist is if the values of the absolute value of f of x grow arbitrarily large as x approaches c, and they don't stay close to any fixed real number. So in other words, when I start to get close to c from both sides of x, those numbers are going to grow really, really, really big. So they're either going to go towards positive infinity or negative infinity. But positive infinity and negative infinity are not numbers. So when the function heads off towards positive or negative infinity, when we look at what's going on from either side of c, we have a special name for it. The third non-existent condition is called an infinite limit. So sometimes functions head towards positive infinity or negative infinity as you get close to that x value. But when this happens, we say that the limit does not exist, but we instead say that f has an infinite limit. So as I get close to c from both sides, I would end up getting values that are growing really, really big in the positive direction or really, really big in the negative direction, in which case I would say that the limit does not exist, but f has an infinite limit. Let's look at the definition of an infinite limit. If f, some function, increases without bound as x approaches c, then we write the limit as x approaches c of f of x equals infinity. So don't be fooled here. Even though we're writing equals infinity, infinity is not a number. So note that in this case, the limit as x approaches c of f of x does not exist, but instead we say that f has an infinite limit. Now similarly, if f of x tends to, this also means approaches, negative infinity, so if this time the function is going towards really big negative values, then we write the limit as x approaches c of f of x equals negative infinity. But again, this limit still does not exist. Alright, so let's go ahead and take a look at an example. So let's say we have the function f of x equals 1 over x squared. So that is one of the 14 basic functions that I gave you, and it's a graph that you should be familiar with. So 1 over x squared looks like this, right? I have this vertical asymptote here at 0. So if I were asked to consider the limit as x approaches 0 of 1 over x squared, so this is x approaches 0, I'd have to look at the two-sided limit. So as I get close to 0 from the left and from the right, what's happening to the y values? So if I know what the graph looks like, I know that as I get close to 0 from the left, my function is going up and up and up and up towards positive infinity. And from the right-hand side, the same thing. I'm going up and up and up towards positive infinity. So what I can say is that the limit as x approaches 0 of 1 over x squared equals infinity, but technically this limit still does not exist because infinity is not a number. Now, if I didn't know what the graph looked like, let's take a quick look at a numerical approach, and we'll only look at it from one side. So let's just create ourselves a little table, and we're going to substitute in x values into the function 1 over x squared. So let's substitute in 0.1, 0.01, and then 0.001. So if I were to substitute in 0.1, and I can go ahead and use my calculator for this if I want. So if I substitute in 0.01, so I have 1 over 0.1 squared, so that's 1 over 0.01. So 0.01 goes into 1 100 times. So we already get out 100, and that's quite different than some of the numbers that we've been coming across in the previous examples. So now let's see what happens when we substitute in 0.01. So 1 over 0.01 squared is going to be 1 over 0.0001, and 0.0001 goes into 1 10,000 times. So 0.01 is going to correspond to 10,000, and I will just let you know that the next value in our table is going to be 1 million. So we can see these values are getting closer and closer to positive infinity as I would continue getting closer and closer to 0 from the right. And as I get closer to 0 from the left, I would also go towards positive infinity. So let's try to summarize our results. So notice that as we got close to 0 from the left, the y values approach positive infinity. As we get close to 0 from the right, the y values get close to positive infinity. So since we approach the same infinity from both sides, we can write or say that the limit as x approaches 0 of 1 over x squared equals infinity. But this limit does not exist. For a limit to exist, the function must approach a number, and infinity is not a number. And now in this next example, we can take a look at infinite one-sided limits. So here we have the function f of x equals 1 over x minus 2. So notice this is the graph of 1 over x with a horizontal shift to the right 2 units. So normally 1 over x has a vertical asymptote at 0, but since the whole graph is shifted to the right 2, now I have this vertical asymptote here at 2. And I want to look at the limit as x approaches 2 from the left side of 2 of 1 over x minus 2. So as I approach from the left side of 2, so numbers to the left of 2, notice what's happening to the y values. My y values are now headed down towards negative infinity. So this one-sided infinite limit says that the limit as x approaches 2 from the left side of 2 is equal to negative infinity. And now if I want to look at the limit as x approaches 2 from the right side of 2, so as I get closer to 2 from the right-hand side, what's happening to my y values is that they're headed towards positive infinity. So the limit as x approaches 2 from the right is positive infinity. Now we've considered the limit from the left and the limit from the right. So now let's look at the limit as x approaches 2 of 1 over x minus 2. So this is a two-sided limit. So notice as I approach from the left, I go to negative infinity, and from the right, I go to positive infinity. So this limit does not exist. Now this is kind of a tricky concept because the limit from the left was negative infinity. Negative infinity is also not a number, so the limit from the left does not exist either. The limit from the right was positive infinity, and the limit from the right did not exist, but we wrote infinity. So here we actually write does not exist because as I approach from both sides, I'm not going toward the same infinity like in the last example. So here the limit from the left doesn't exist, but goes towards negative infinity. The limit from the right doesn't exist, but the y values go towards positive infinity. And then as I approach from both sides, they're not going to the same infinity, so I just have to put does not exist. And now in this next example, I can consider the natural log function, and this is one of those basic functions that you should know the graph of. And you should also know there's a vertical asymptote at 0 on the natural log function. So here, as I approach 0 from the right-hand side, so here's 0. So as I approach 0 from the right, what's happening to the y values is that they're going down towards negative infinity. And since the function natural log is not defined for values on the right side or on the left side of 0, negative values, this is the only one-sided limit that we can consider for the natural log function. So the limit as x approaches 0 from the right of natural log is negative infinity. But again, this is an infinite limit, so the limit really does not exist. So hopefully throughout this video you've noticed that the functions that we've analyzed have all had vertical asymptotes, and there's a reason for that. So the formal definition of a vertical asymptote is a line x equals a is a vertical asymptote of the graph of a function y equals f of x if either the limit as x approaches a from the right of f of x equals either positive or negative infinity, or the limit as x approaches a from the left of f of x equals positive or negative infinity. So vertical asymptotes formal definition really has to do with infinite limits. So as I approach a, so let's draw a quick sketch of any graph here that has a vertical asymptote. So let's go ahead and say that there's a vertical asymptote at some value, call that value a. So if we draw any function, this is a vertical asymptote provided that as I get close to a from some side, I'm headed towards some infinity. So as long as this is happening, I'm getting close to a from the left side, I'm going towards an infinity, then a is considered to be a vertical asymptote, or more specifically, x equals a. So whenever you write a vertical asymptote, it has to be of the form x equals some number. Or I could also have the function going down towards negative infinity as I get closer to a from the left. Or I could have the function go towards positive infinity as I approach a from the right, or down towards negative infinity as I approach a from the right. So as long as any one of these four possibilities is happening on the graph, then x equals a is a vertical asymptote of the function y equals f of x.